Hello everyone, myself Pavitra Vyas from Department of Information Science and Engineering, Sri Venkateshwara College of Engineering. Now I'm going to explain about mutation analysis and fault-based adequacy criteria. Mutation analysis. What is mutation analysis? A mutation analysis is a form of white box testing in which the testers change some specific components of an application's source code to ensure a software test suite will be able to detect the changes. Mutation analysis is the most common form of software fault-based testing. A fault model is used to produce hypothetical faulty programs by creating variants of the program under test. Variants are created by seeding faults, that is, by making a small change to the program under test following a pattern in the fault model. The patterns for changing program text are called mutation operators. Each variant program is called a mutant. Here are some terminologies which include in the mutation analysis. Firstly, original program under test, which means the program or the procedure to be tested. Mutant, a program that differs from the original program for one syntactic element. Example, a statement, a condition, a variable, or a label. Syntactic, which means according to the syntax. Distinguished mutant, a mutant that can be distinguished for the original program by executing at least one test case. Equivalent mutant, which means a mutant that cannot be distinguished from the original program. Mutation operator, a rule for producing a mutant program by syntactically modifying the original program. Mutants should be plausible as faulty programs. Mutant programs that are rejected by a compiler or that fail almost all tests are not good models of the faulty we seek to uncover with systematic testing. We say a mutant is valid only if it is syntactically correct. A mutant obtained from the program of figure 1.1 by substituting while for switch in the statement at line 13 would not be valid since it would result in a compile time error. We say a mutant is useful only if, in addition to being valid, its behavior differs from the behavior of the original program for no more than a small subset of program test cases. A mutant obtained by substituting 0 for 1000 in the statement at line 4 in the figure 1.1 would be valid but not useful since the mutant would be distinguished from the program under test by all inputs and thus would not give any useful information on the effectiveness of a test suite. Defining mutation operators that produce valid and useful mutations is a non-trivial task. Since mutants must be valid, mutation operators are syntactic patterns defined relative to particular programming languages. Figure 1.1 shows some mutation operators for the C language. Constraints are associated with mutation operators to guide the selection of test cases likely to distinguish mutants from the original program. For example, the mutation operator SVR, that is scalar variable replacement, can be applied only to variables of compatible type, that is to be valid, and a test case that distinguishes the mutant from the original program must execute the modified statement in a state in which the original variable and its substitute have different values. Here is a program which converts line endings among the Unix DOS. The main procedure which selects the output line, end conversion, and the output procedure emit are not shown in this program. Firstly, void transduce. It defines buffer length, that is the 1000 character buff length. It accumulates the line into this buffer. Int position is equal to 0. Character in char, that is the next character from input. Int at cr is equal to 0, while in character is equal to get char, which is not equal to evof. Evof is nothing but end of file. Switch of in char case lf. lf, it is a short for line feed. It includes an ASCII character or a button on the printer that instructs the printer to move down one line. If of at cr is equal to 0, else emit buff comma position, whereas position is equal to 0, and then break. Case cr, emit buff comma position, where position is equal to 0, at cr is equal to 1, and then break. Default, if position is greater than or equal to buff length of 2, then fail. It gives an output as buffer overflow. Buff of position increment is equal to in char. If position is greater than 0, emit buff comma position, and it ends. Here are some IDs which are included with its description and the operator. Firstly, CRP, constant for constant replacement, which has a description of replace constant C1 with constant C2. SCR, scalar for constant replacement, which has a description of replace constant C with scalar variable X. ACR, array for constant replacement, which is replace constant C with array reference A of I. SCR, construct for constant replacement. SVR, scalar variable replacement, which describes replace scalar variable x with a scalar variable y. CSR, constant for scalar replacement variable. ASR, array for scalar variable. SSR, construct for scalar replacement, which describes replace scalar variable x with struct field s. CAR, constant for array replacement, which has a description replace array reference A of I with constant C. SAR, scalar for array replacement, replace array reference A of I with scalar variable x. Moving on to the next topic, fault-based adequacy criteria. Fault. Fault is nothing but which arises when the expected result don't match with the actual result. Here, a program and a test suite mutation analysis consists of the following steps. First step includes select mutation operators. If we are interested in specific classes of faults, we may select a set of mutation operators relevant to those faults. Generate mutants. Mutants are generated mechanically by applying mutation operators to the original program. The third step is distinguish mutants. Execute the original program and each generated mutant with the test cases in T. A mutant is killed when it can be distinguished from the original program. A mutant can remain live for two reasons. Firstly, a mutant can be distinguished from the original program, but the test suite T does not contain a test case that distinguishes them. That is, the test suite is not adequate with respect to the mutant. The mutant cannot be distinguished from the original program by any test case. That is, the mutant is equivalent to the original program. Here is given a set of mutants Sm and a set test suite T. The fraction of non-equivalent mutants killed by T measures the adequacy of T with respect to Sm. Unfortunately, the problem of identifying the equivalent mutants is undecidable in general, and we could err either by claiming that a mutant is equivalent to the program under test when it is not, or by counting some equivalent mutants among the remaining live mutants. The adequacy of the test suite TS evaluated with respect to the 4 mutants of figure 1.2 is 25%. However, we can easily observe that mutant Mi is equivalent to the original program. That is, no input would distinguish it. Conversely, mutants Mk and Ml seem to be non-equivalent to the original program. There should be at least one test case that distinguishes each of them from the original program. Thus, the adequacy of TS measured after eliminating the equivalent mutant Mi is 33%. Mutant Mi is killed by the test case mixed, which represents the unusual case of an input file containing both DOS and Unix terminated lines. DOS is nothing but a disk operating system. We should expect that mixed would also kill MK, but this does not actually happen. Both MK and the original program produce the same result for mixed. This happens because both the mutant and the original program fail in the same way. The use of simple oracle for checking the correctness of the outputs. Example, checking each output against an expected output would reveal the fault. The test suite TS2 obtained by adding test case mixed to TS would be 100% adequate relative to this set of mutants after removing the fault. Here are some test case IDs. Firstly, MI, operator ROR, line 28. The original or the mutant is position is greater than or equal to buff length minus 2, or position is equal to buff length minus 2. Secondly, MJ ROR 32. Position is greater than 0. Position is greater than or equal to 0. Test case 1D, 2U, 2D, 2M indicates X. MK SDL 16 line at CR is equal to 0, nothing. Here all the test cases are empty. MI SSR line 16 at CR is equal to 0, position is equal to 0. Mixed test case indicates X. X indicates the mutant is killed by the test case in the column head. Here is the description of each test case. Firstly, 1U, 1 line Unix line end. 1D, 1 line DOS line end. 2U, 2 lines Unix line end. 2D, 2 lines DOS line end, 2M, 2 lines MAC line end, last line not terminated with the line end sequence, long, very long line greater than the buffer length, mixed, mix of DOS and Unix line ends in the same file. Here I complete with my topic. Thank you. Have a nice day.